Our vast universe is home to phenomena such as star-devouring black holes, rapidly rotating pulsars, radiant nebulae birthing stars, and countless galaxies. Yet it may not be endless. There could be a distinct edge, a cosmic boundary. Let's embark on a journey to that possible frontier. Visualize the universe as a massive layered structure. At its core is Earth, enveloped by our solar system, which is in turn housed inside a galaxy within this grand universe. As we journey beyond our solar system, passing by the planets from Mars to Neptune, we encounter the heliosphere. Here, the solar wind's velocity plunges dramatically, giving way to the near-stagnant wind at the heliopause. Beyond, the ship faces the force of the interstellar wind. Two remarkable emissaries from Earth, Voyager 1 and Voyager 2, now reside in this region. They revealed the heliosphere's uneven shape. Venturing further, an asteroid belt known as the Oort cloud becomes visible, believed by some scientists to source Earth-bound comets. Beyond lies the expansive Milky Way, spanning around 106,000 light-years. Guiding our journey is a cosmic map, identifying our location in the Laniakea supercluster. However, there's more. At a greater scale, the Hydra Centaurus supercluster emerges. At the universe's maximum observable scale, a surprising revelation awaits, evidence suggesting a universe boundary. This edge, located an astounding 10 billion light-years away, is a testament to time and evolution. During such a lengthy voyage, our sun might wither or explode, and the Milky Way might merge with the Andromeda Galaxy. Our endpoint is the Eridanus supervoid, a vast empty stretch spanning 1 billion light-years. This void might result from an unfathomable collision, our universe meeting another. This leads to a tantalizing notion of multiple universes, where every choice leads to alternate outcomes in parallel realities. Imagine our universe as a bubble. Eons ago, another bubble universe brushed against ours. Their gravitational interplay caused cosmic distortions. As they separated, a piece of our universe might have been taken, leading to the creation of the Eridanus supervoid. Eridanus supervoid covers a region of space about 1 billion light-years in size. This makes it one of the largest known voids in the universe. This superwave is associated with the so-called cold spot in the cosmic microwave background radiation. The temperature in this spot is lower than the average temperature of the background radiation. The exact origin and nature of Eridanus supervoid is still a subject of research. This object provides scientists with a unique opportunity to study the structure and evolution of the universe on large scales. Yet, perceiving the universe's entirety remains a challenge. Like an ant on a basketball, we see a consistent horizon due to our 3D viewpoint. But adding dimensions could change our perceptions. Could black holes, with their powerful gravitational influence, offer a passage to these other realms? The vast expanse of our universe is filled with intriguing structures, mysteries, and phenomena that continually challenge our understanding of the cosmos. The Eridanus supervoid, with its immense size and enigmatic nature, stands as a testament to the universe's capacity to astonish and confound us. And for those intrigued by the enigmatic nature of black holes, we invite you to explore more in our other videos. Dive deep into the mysteries of these cosmic giants and join us on a journey of understanding and wonder. Stop whatever you're doing for a moment and think about this. Where are we going? I don't only mean you or me. I mean our planet and the entire solar system. We've been traveling through space for eternity, but does this journey have any aim or destination? The solar system is moving at a speed of 450,000 miles per hour. Our beautiful blue Earth is snugly tucked inside it, and it seems that our region is quite calm and safe, not like some terrifying experiences our celestial neighbors go through. But where are we going? Just wandering around in a giant circle? Not really. Apparently, our galaxy, as well as several nearby galaxies, are being pulled toward a certain region of space. It's about 150 million light-years away. The worst thing is that we do not know what exactly it is. That's why we call it simply the Great Attractor. This bizarre area is, unfortunately, on the other side of the Milky Way. That's why we can't see it. This region of the sky is known as the Zone of Avoidance, and it's part of why the Great Attractor is so mysterious. This zone lies in the general direction of the center of our galaxy, and there's too much dust and gas there for us to see far in the visible spectrum. But astronomers can see enough to understand that our galaxy, as well as nearby galaxies, are all moving toward the Great Attractor. It means that something must be making things hurtle in that direction. Could it be a gargantuan black hole hidden in the darkness of the cosmos, pulling things toward it and munching on them? Or is it something even stranger and more dangerous? What we know for sure is that this something is immensely massive. For the first time, evidence of the existence of the Great Attractor was discovered in the 1970s. At that time, scientists didn't have the needed equipment to see through the zone of avoidance. That region blocks most of the visible light coming from beyond. But the good news is that this gas and light can't block all infrared and X-ray light. So when X-ray astronomy became more powerful, people got the opportunity to sneak a peek at objects dwelling in that region. It turned out there was a huge supercluster of galaxies in the region of the Great Attractor. It's now known as the Norma clusters. This enormous structure, consisting of thousands of galaxies, has a mass of around 1,000 trillion suns. So, the Norma cluster is massive, that's true, and local galaxies seem to be moving toward it. And still, it doesn't explain all the movements in that region. And now, I'll tell you something even more puzzling and spooky. The mass of the Great Attractor, whatever it is, isn't enough to account for the pull. If we take an even larger region of galaxies, it will become clear that both the Great Attractor and local galaxies are moving toward something even larger. This space behemoth is known as the Shapley supercluster. It's made up of more than 8,000 galaxies and is as massive as 10 million billion suns or even more. This supercluster is the greatest galaxy cluster we know about within 1 billion light years. And everything in the universe, Earth, the solar system, even the Great Attractor, are moving toward it. But at the moment, astronomers are still trying to find more information about the Great Attractor. The Hubble Space Telescope is now focused on the region of space where it resides. The largest galaxy visible in the region of the Norma cluster is ESO 137002. It's a spiral galaxy with large clouds of dust across the galaxy's bulge. Unfortunately, Hubble, being an optical telescope, can't see a tail of glowing X-rays extending out of the galaxy. And in general, observing the Great Attractor is difficult at optical wavelengths. The plane of the Milky Way both outshines and obscures with dust many objects located behind it. And even though we can get some information thanks to infrared or radio observations, the region behind the center of the Milky Way remains an almost complete mystery.
According to the theory of panspermia, life could have been brought to Earth by a meteorite, comet, or asteroid from a different region of space. At the moment, this idea remains purely theoretical. But let's figure out if it could actually turn out to be true. Traditionally, exobiologists, those who are focused on searching for life outside Earth, have been trying to explore the possibility of life on Mars or in the subsurface oceans of Saturn's and Jupiter's icy moons. But simple life could be much more widespread. It could be drifting through interplanetary space right now, in the form of dormant bacteria and spores. Several scientists have noted that the ultra-harsh environment of space is likely to severely damage the DNA and RNA of such spores and microorganisms. Others believe that since enough microbes could be traveling in a dust cloud, some of them could survive in their original form. There are several types of panspermia. For example, lithopanspermia proposes that some kind of microbic life could exist in debris blasted into the cosmos after planetary collisions with comets and asteroids. Radiopanspermia claims that organisms might be able to travel through space with the help of radiation coming from stars. But in this case, it's unclear how the effect of dangerous ultraviolet and X-ray radiation, combined with the vacuum of space, doesn't totally destroy microorganisms. There's also pseudopanspermia. According to it, organic building blocks of life appear in interstellar clouds of dust. They get transported to the surfaces of planets, and life starts developing there. It sounds really fascinating, but is there any evidence for the panspermia theory? Well, there have been a few orbital experiments. For example, from 2008 to 2016, the samples gathered by EXPOSE, special equipment mounted outside the International Space Station and dedicated to astrobiology, were exposed to the conditions of space. After that, they were returned to Earth from the ISS. It turned out that some of them had survived those severe conditions. There was even a case when 100% of bacterial spores placed in Mars-like conditions were still capable of life. Also, some seeds survived and were later grown as plants on Earth. There have also been exostack experiments on the U.S. Long-Duration Exposure Facility satellite and biopan experiments on Russian photon capsules. They have shown that with minimal protection, spores, lichens, and even minuscule animals, such as tardigrades, might be able to survive in space for as long as several years. A piece of Surveyor 3 lunar lander was brought back to Earth in 1969 by the Apollo 12 mission. Shockingly, it contained an Earth bacterium that had survived unprotected for more than 2 years on the airless surface. At the same time, this bacterium could have come from laboratory contamination on arrival back on Earth. The Indian Space Research Organization carried out a search for space microorganisms too. It was done at stratospheric altitudes via balloon flights. The results showed that living interplanetary cells existed in air samples taken from heights of above 25 miles. Normally, air from lower levels of the atmosphere can't be transported there, so this discovery seemed to prove the theory of panspermia. But in 2010, NASA atmospheric sampling before and after hurricanes proved that under certain circumstances, Earth bacteria could actually be transported very high into the upper levels of the atmosphere. One of the main arguments against panspermia is that if this theory was correct, all life found throughout the solar system would have a common origin and share main biochemical characteristics like genetic code. It doesn't sound plausible. Many specialists believe that only the presence of astronaut explorers on the surfaces of, let's say, Mars, Europa, or Enceladus can properly solve the question of life in the solar system. They can compare any life forms found with Earth-type life, which can turn out to be a real test of panspermia. In any case, until probes finally find direct proof of spaceborne life, the panspermia theory will remain unproven.
The universe is believed to have started around 14 billion years ago with a Big Bang. And as far as we know, it hasn't stopped expanding since then. But if it's so, the universe must have started somewhere, right? And there has to be the center of the universe somewhere out there. Well, experts claim there's no center of the universe. Neither is there any center of the expansion. It's the same everywhere. You see, it's wrong to imagine the Big Bang as an ordinary explosion, and the universe does not expand from the center outward. Instead, as far as we know, the universe is expanding equally in all places. In 1929, Edwin Hubble said he had managed to measure the speed of galaxies that were located at different distances from Earth. He discovered that the farther they were, the faster they were moving away from us. Does it mean we are at the center of the expanding universe? Unlikely. It just means that the universe is expanding at the same rate everywhere. And wherever you are, it will seem to you that you're at the center of the universe. Now, about that Big Bang. If you watched a regular explosion in slow-mo, you'd see material expanding out from a central point. Right after the explosion, the center remains the hottest point. Later, a spherical shell of material starts growing, moving away from the center of the explosion. The process continues until gravity stops this expansion. But the Big Bang was nothing like that. It was an explosion of space, not an explosion in space. According to the most common theory, there was no before to speak of, no space and no time. It means that the Big Bang was very different from anything we're used to and doesn't have any central point. Even if we had been able to observe it in real life, we wouldn't have seen an expanding edge with empty space beyond it. The only thing we can detect now is a faint background glow. It was left by the hot primordial gases that existed in the early universe. This is called cosmic background radiation, and it's uniform in all directions. It can mean only one thing. It's not matter moving outward from one point, but space itself expanding evenly. At the same time, the idea that the universe is expanding uniformly in all directions doesn't rule out the possibility that somewhere out there, there's a denser and hotter place that might be called the center of the universe. But as far as we can see, there's no sign of such a special point. The theory that the universe should be uniform is known as the cosmological principle. It appeared in 1933. Not so long before that, some scientists believed that the universe only consisted of our home galaxy. If this was the case, we could definitely consider the center of the Milky Way to be the center of the universe. But in 1924, Hubble put an end to that debate. He showed there were other galaxies besides our own. But in any case, how we see the universe is limited by the speed of light and the finite time since the Big Bang occurred. Even though the observable part of the universe is very large, it's likely tiny in comparison to the entire universe, which may be infinite. The universe might have many shapes, with or without an identifiable center. And if it turned out to have a center outside of the observable universe, this point, or region of space, could be just one of many. It could be just like the center of our galaxy, which was considered to be the center of the universe before.
A Dyson sphere is a theoretical megaproject, a ginormous sphere encircling a star with platforms orbiting in tight formation. It's supposed to be an ultimate solution both for energy production and living space. The creators of a Dyson sphere get a lot of surface area for habitation and the ability to catch every tiny bit of solar radiation and heat produced by their central star. The first person to theorize about such a bizarre construction was British-American theoretical physicist Freeman Dyson. According to him, an intelligent extraterrestrial civilization could consider building this sphere after colonizing some moons and planets in their local stellar neighborhood. With the growth of their population, these aliens would need more and more energy to sustain their lives. Dyson calculated that assuming that this alien society grew at 1% per year, their area and energy needs would become 1 trillion times larger in a mere 3,000 years. And if their solar system contained a space body similar in size to Jupiter, they could take it apart and spread its mass in a spherical shell by building a structure at twice the distance between our planet and the Sun. This amount of material would be sufficient to build a huge number of orbiting platforms. Each of them could be 6 to 10 feet thick, which would basically allow this civilization to live on their star-facing surfaces. A shell this thick could be comfortably habitable and capable of holding all the equipment needed for using solar radiation without falling onto the star from the inside. But after absorbing all this solar energy, the sphere would have to re-radiate it. Otherwise, the energy would build up, eventually causing the construction to melt. It means that the light of a star wrapped in a Dyson sphere would look dimmed or even completely darkened, depending on how dense the platforms orbiting it were. At the same time, it would glow unusually bright in infrared wavelengths invisible to the unaided eye. Because of this infrared radiation, Dyson spheres are classified as a type of technosignature. It's a sign of activity that astronomers can use to discover intelligent life forms in the universe. Some Earth-based researchers have infrared maps of the night sky they examine in hopes of spotting Dyson spheres. So far, no one has ever found one. However, one study has selected several Dyson sphere candidates. Its authors have processed large amounts of information using a special data pipeline for combining and analyzing information. One of the main search criteria is the detection of excessive infrared radiation. At the same time, it's important to distinguish this radiation from that emitted by natural objects. After a complicated filtering of millions of objects, the researchers identified 7 potential Dyson spheres. Sure, further analysis is needed to determine their nature. To do this, scientists want to use optical spectroscopy, which may reveal more details about these objects and their origins. At the same time, the researchers admit that these candidate Dyson spheres might have other explanations. For example, they could be debris disks or protoplanetary disks of young stars. Only more research can show whether we can find traces of other civilizations among star systems. For now, it's still an open question. Interestingly, Dyson spheres have been spoken about a lot in science fiction. As far back as 1937, a novel called Star Maker by Olaf Stapledon described systems in one particular galaxy that were surrounded by a gauze of light traps, which focused solar energy for intelligent use. That was the reason why the entire galaxy was dimmed. In another novel, Ring World, the writer spoke about a ring-shaped artificial structure surrounding a star.
Even though it may seem that science has reached the level where there are no more mysteries left, it's not exactly true. And no modern physicist would dare to assume that our knowledge of the universe is near completion. What are scientists still wondering about? Let's figure it out. For one thing, dark energy keeps puzzling researchers even today, because the universe doesn't seem to add up. Even though gravity is pulling space-time, the very fabric of the cosmos, inward, the universe keeps expanding outward, and this process is speeding up. That's how the concept of dark matter was born. It's believed to be some invisible agent that counteracts gravity by pushing space-time apart. It goes like this. The universe expands, and more space appears out there, and with it, more dark energy. According to astronomers, this invisible energy must make up more than 70% of the universe. But no one knows how or where to look for it. Then there's dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Scientists call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. Its existence is inferred from the effects it has on visible matter, radiation, and the very structure of the universe. There are a few special detectors on the lookout for weakly interacting massive particles, of which dark matter might be composed. But so far, nothing has been found. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Then, there's the question of antimatter. It's the oppositely charged and oppositely spinning twin of good old matter. The intrigue here is why there is more matter than antimatter in our universe. It would be logical to assume that the universe would want to treat matter and antimatter equally. Thus, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced, right? Not really. If it had happened, there would have been a moment of total annihilation. Protons would have canceled antiprotons, electrons, anti-electrons, and so on. It would leave behind a lifeless, matterless expanse of space. Luckily, for some mysterious reason, when the universe was created, there was some excess matter. It didn't get annihilated, and that's how everything started. But there's still no accepted explanation for this. Then, we've got particle physics questions. They account for many unsolved problems. Sonoluminescence is one of them. Let me explain. Let's say you take some water and hit it with sound waves. It forms bubbles, low-pressure regions surrounded by high pressure. Once the outer pressure pushes on the lower pressure air, the bubbles collapse. But while collapsing, they emit light, even though the flashes don't last for more than a trillionth of a second. What bothers scientists is that it's unclear what the source of this light is. There are a few theories, of course. Some experts think tiny nuclear fusion reactions might be involved in the process. Others believe some kind of electrical discharge comes into play here. There's also the idea of compression heating of the gases inside the bubbles. None of these theories have been accepted yet. This might sound surprising, but we haven't figured out what exactly gravity is either. Other forces are mediated by particles, but not gravity. Some physical theories claim that it might be carried by a hypothetical massless particle called a graviton, but no one has seen these gravitons yet. We don't even know what kind of detector can be built to spot them. Even if gravitons come into contact with matter, and we aren't sure about it, they do it extremely rarely. There's also a theory that gravitons are closed loops of energy, but again, it's just a theory so far. There are tons of other unanswered questions bothering our minds. What happens inside a black hole? Is string theory correct? What is the fate of our universe? Do we live in a false vacuum? Hopefully one day we'll find the answers to all these mysteries.
Imagine living in a world where technology has reached its highest point. Your daily routines are orchestrated by an AI, which anticipates your every need, from brewing your morning coffee to selecting a perfect evening outfit. The cityscape outside the window of your floating home is a marvel of efficiency. Flying pods whisk people to their destinations. Renewable energy sources power the giant mega-city, creating an environment of pristine streets and clean air. At work, you have online meetings with colleagues living across galaxies, collaborating on projects that go beyond our current understanding. It sounds like a sci-fi story, but some extraterrestrial civilization might have already reached this level of development. Scientists started pondering the possibility of life beyond Earth long ago. They've been wondering what such life could look like and how humans could identify it from afar. This train of thought led to the development of several classification systems, including one called the Kardashev scale. It was proposed in 1964. This classification evaluates hypothetical alien civilizations based on how much energy they are able to harness. According to the scale, there are 3 types of civilizations. The first type is a technological level close to the current level of Earth. Type 2 is a civilization capable of harnessing the energy emitted by its own star. And the third type is a civilization that has learned to use the energy of an entire galaxy. This scale sure caught people's imagination. It was included in a 5-page paper called Transmission of Information by Extraterrestrial Civilizations. This work focuses on calculating how powerful a light signal from any point of the universe should be for us to detect it. Now, within the basic categories, humans are a Type 1 civilization on the Kardashev scale. But some experts claim we aren't even a 1, since we haven't managed to harness the equivalent of the entire energy of Earth. This makes us more like 0.7, and of course, we're far from being a 2, a civilization with a working Dyson sphere. A Dyson sphere is a theoretical mega-engineering project encircling a star with platforms that are orbiting it in a tight formation. It might be the ultimate solution for living space and energy production. With its help, the creators of this ginormous construction could have loads of surface area for living and the ability to capture every tiny bit of solar radiation produced by their main star. As for a Type 3 civilization, it extracts fusion and exotic energy, information, and raw materials directly from their galaxy. This civilization is capable of space travel via wormholes, intergalactic communication via subspace, and galaxy-scale influence. They have supreme access to energy and are spread all over the universe. After millions of years of evolution, a Type 3 civilization may actually be AI superintelligences. Androids, cyborgs, and humans may be considered subspecies in such a highly advanced galactic society. In the most hopeful scenario, humans would have found a way to coexist with their AI masters. Or there might be no humans in that world whatsoever. This civilization might have already ascended into beings of pure energy, capable of controlling and directing machines to carry out all kinds of work. Now, back to the Kardashev scale. Even though it focuses only on technosignatures, it acknowledges biosignatures too, suggesting that each search should inform the other. The discovery of the simplest organism, for example, on one of Saturn's moons, could increase the probability that many Type 2 civilizations exist in our galaxy. At the moment, SETI is the main player in the field of looking for extraterrestrial civilizations. It's a combined effort of enthusiast scientists who focus on receiving and analyzing signals from space in the radio and visible light regions of the electromagnetic spectrum. It's looking for non-random patterns that have been likely sent deliberately by technologically advanced beings. The first modern SETI search was Project OMA in 1960. It used a radio telescope in Green Bank, Virginia. SETI uses targeted searches concentrating on groups of nearby sun-like stars.
So, astronomers have just announced that they might have found signs of possible life on a planet outside our solar system. Wow! This distant world is called K2-18b, and it sits about 124 light-years away in the Leo constellation. So, what life are we talking about? Little green men? Octopus-like tentacled creatures? Well, not exactly. First things first, let's define what life is. It's what distinguishes animals and plants from inorganic matter, like the ability to grow, reproduce, and change. Now, what do we need to support life? If what comes to your mind is water, bingo! Scientists have the feeling that K2-18b might be covered in oceans, and if it's so, it can support tiny forms of life like microbes. A team of researchers from the UK and the US used the James Webb Space Telescope to look at the planet's atmosphere. They found hints of two very special chemicals. On Earth, only living things can produce those, and the living things I'm talking about are mostly tiny ocean plants called phytoplankton. So, basically, this planet might indeed host life in the form of algae. Now, of course, scientists still need more proof before getting too excited. We should keep in mind that it's possible that those chemicals were made by something we don't understand yet, not necessarily by living things. But still. K2-18b is a big boy. It's more than 8 times heavier than Earth and about 2.5 times larger. So, what makes it even more interesting is that it's located in the Goldilocks zone around its star. That means it's not too hot and not too cold there, just right for the existence of liquid water, which is highly important for life, as we know it. Astronomers study faraway planets like this by watching how their light changes when they pass in front of their star. This allows us to figure out what kinds of gases are in the planet's atmosphere. Back in 2013, the James Webb Space Telescope found methane and carbon dioxide in the atmosphere of the planet. These are carbon-based molecules, and it was the first time they were found on a planet in the habitable zone. Scientists also saw a weak signal of a chemical called DMS, which is mostly made by tiny ocean life here on Earth. So, the researchers pointed the telescope at the planet again a year later using a different tool that could pick up more light details. This time, they found much stronger signs of DMS and some related chemicals. But the problem is the signals aren't strong enough yet. They haven't reached something called the 5 sigma level, a parameter scientists use to confirm discoveries. Plus, even if the DMS really is there, it doesn't automatically equal the existence of life. Scientists once found DMS on a comet, which means that it can be produced without some kind of life taking part in the process. And still, the amount of DMS on K2-18b looks way higher than anything seen on Earth. That's why some astronomers are sure it's coming from something living. K2-18b has been a top pick for what scientists call a Hycean planet. This term means a big, watery world with thick hydrogen atmosphere. It's not the kind of place where extraterrestrial civilizations like in movies would live. But it could be home to tiny life forms, like the microbes that once lived in Earth's oceans billions of years ago. Once again, not everyone agrees on how friendly K2-18b really is for life. Some scientists think planets like this might actually be too close to their stars to hold on to liquid water. K2-18b orbits its star every 33 days, which is pretty fast, and could mean it's too hot. That's why some experts claim that even if the planet has any water at all, it might be boiling. Or maybe it's not water, but oceans of lava. But most scientists agree on one thing: we should wait and see. With just 16 to 24 more hours of telescope time, astronomers could confirm what they've seen. This could happen in the next few years. And even if it turns out K2-18b isn't the world we're looking for, we're still getting close. With powerful telescopes like James Webb and more coming in the future, we might be able to answer whether we're alone in the universe or not. At the same time, some places in our own solar system, like Mars, Venus, or Saturn's moon Enceladus, might actually have a better shot at hosting life. Or we could keep exploring other promising worlds, like Proxima Centauri b, which is the closest exoplanet we know about. It's just 4.25 light-years away from us and orbits a small star called Proxima Centauri, right in the habitable zone. This planet is a bit bigger than Earth, which makes it a super-Earth. That's what we call exoplanets larger than ours, but much smaller than gas giants like Neptune or Jupiter. Proxima Centauri b is a fast-moving world. It needs a mere 11 days to go all the way around its star. Scientists think Proxima Centauri b might have a rocky surface, and that's a good sign for possible life. On the other hand, its star blasts it with a lot of ultraviolet radiation. It might have already destroyed the planet's atmosphere, if there was any to begin with. So there's a big question mark when it comes to this world's habitability. Then we've got TRAPPIST-1e, another promising Earth-like planet. It's one of 7 rocky planets orbiting a small cool star called TRAPPIST-1, about 39 light-years away. Discovered in 2017, it might be one of the most promising places to look for life beyond Earth. This planet is actually a bit smaller than Earth, with a mass around 1/2 that of our planet. It completes an orbit around its star in just 6 days, which is super fast compared to Earth's 365 days. The planet's size and density suggest it has a rocky surface, and that's another key factor when we talk about habitability. Even though TRAPPIST-1e is very close to its star, the star is quite dim and cool, so the planet might still have a stable Earth-like climate. Some scientists even think it could have more water than Earth. Let's move on to Kepler-186f, located about 500 light-years away. It was the first Earth-sized planet found in a habitable zone of another star. It orbits a red dwarf, which burns cooler and lives much longer than our Sun. This means Kepler-186f could have stable conditions for billions of years, giving life plenty of time to possibly form and evolve. The planet gets only about 1/3 of the sunlight Earth receives, so it would likely be cooler but still warm enough to keep water from freezing. It also seems to be a rocky planet just like Earth, which boosts its chance of hosting life. Now, how about visiting LHS 1140b, about 40 light-years away? This planet has about 5.5 times the mass of Earth. Scientists think it's rocky and possibly has a thick atmosphere, which is a big deal. An atmosphere like that can trap heat, keep temperature stable, and protect water from escaping into space. This world orbits a quiet red dwarf star, so it's not constantly blasted by harmful flares like some other exoplanets are. Some studies even suggest LHS 1140b could be an ocean world with lots of water. So it's one of the more exciting planets we've found in our neighborhood. And finally, we have Gliese 12b. Astronomers call it Exo-Venus. It sits 40 light-years away from Earth. This world is about the size of Venus and orbits a cool red dwarf star. It needs just under 13 days to complete one orbit. The temperature on the planet is around 107 degrees, which is quite warm but still okay for life. The thing that makes Gliese 12b so interesting is that it could help us understand how Earth-sized planets around cool stars hold on to their atmospheres. That's important because an atmosphere is crucial for things like liquid water and protecting life from harmful radiation. According to some researchers, Gliese 12b is one of the best chances we have to figure out whether planets like this can stay habitable. The search for ET is on. It's most definitely on. With the successful launch of the James Webb Telescope, the search for Earth-like planets has become a riveting topic of worldwide attention. Apart from the James Webb Telescope, other tools are being used to find good Earth-like candidates. The TESS satellite and the Kepler telescope are at the forefront of searching for other Earths. After we first clear the air of a few pesky philosophical questions, we'll take a close look at these two searches and what the James Webb Telescope hopes to find. So, why are we searching for Earth-like planets? Well, because we can. Incredible advances in Earthbound telescope technology have enabled ultra-precise observations of starlight, which led to the earliest discovery of exoplanets. As planets go around stars, there's a gravitational interaction between the planet and the star. They pull each other. The planet's pull upon the star will cause the starlight to wobble back and forth ever so slightly as the planet or planets orbit the star. This has always been the case, but the wobble of the starlight was never able to be detected, because starlight always twinkles. Twinkle, twinkle, etc. Adaptive optics inside telescopes is the technological breakthrough that first enabled astronomers to find exoplanets by taking the twinkle out of starlight. Mechanical springs on the underside of telescope mirrors bend the mirrors ever so slightly to neutralize the distortion, the twinkle, caused by starlight passing through Earth's atmosphere. Without the glimmer of starlight, the slight wobble caused by planets pulling gravitationally on the stars is observable. The bigger the wobble, the more planets. It's called the astrometric method of exoplanet detection. Isn't that a mouthful? Whole star systems and literally thousands of exoplanets were inferred to exist around nearby stars by analyzing the wobbly patterns of starlight. But the planets themselves could not be seen. Suddenly, our solar system was not unique anymore. Astronomers got giddy over the inescapable conclusion that probably every star had planets. It became impossible not to ask the poignant question, is the Earth unique, or are there other Earths? What's the big deal about finding Earth-like planets anyways? Well, considering all the financial resources the developed countries are spending on finding Earth-like planets, it can be said without a doubt that it's definitely a big deal. Including the launched James Webb Telescope, which cost $10 billion, the Kepler Space Telescope, which cost $550 million, and the TESS satellite, which cost $200 million. The investment in finding Earth-like planets is certainly eyebrow-raising. Now, if you keep in mind that these costs are just for the hardware, and to get a sketch of the full magnitude of the search, you must also include the salaries of a team of data miners, PhD analysts, and postgrads all across the globe in universities, national space agencies, and private institutions. We will conclude that finding another Earth is truly an immense undertaking. Now, suppose we find one. Then Earth is not alone anymore. It's not that we can actually go to any of these planets anytime soon. Interstellar travel requires some breakthroughs in physics and technology, and, well, we aren't there yet. But knowing that there are planets out there in the Milky Way that are like Earth in all the essential respects, like liquid water, oxygen, and habitability, will make space less foreboding, more welcoming, more exciting to study and explore. It may also give us more pride in our home planet and make us all better Earthlings. The triple mission looking for other Earths, the Kepler telescope, the TESS satellite, and the James Webb telescope use distinct approaches to find exoplanets. And the synonym TESS tells us what that method is. The T stands for transiting, and that's the key to the whole exoplanet search. E stands for, you guessed it, exoplanets, the target of the excellent investigation of another Earth. S stands for survey, because TESS looks at hundreds of thousands of nearby stars. And S stands for satellite, because TESS is orbiting Earth, unlike the James Webb Space Telescope, which will orbit the Sun. When a planet passes in front of a star, that is called a transit. The planet will block some of the light coming from the star. This decrease or dimming of the star can be measured. The dimming of starlight tells lots of things about the planet. By knowing how bright the star is and how much the star's light was dimmed by a transition in front of the star, we can tell how giant the planet is or how close it is. But we won't know which. Is it big or is it close? Until the planet's orbit is also timed. It means our TESS satellite must take long-duration videos of the stars. Ooh, video of the stars. Hollywood should like that. The TESS satellite doesn't have a telescope. It uses 4 CCD cameras to stream live long-duration videos of as many stars as possible, hundreds of thousands of stars. Why so many? Well, because for a transit of a planet to be observed, it must pass directly between the TESS satellite's cameras and the star. If the planet is not on the exact line-of-sight angle between the star and TESS's cameras, it cannot be seen because it will not cut off any starlights. Planetary transits are rare. For example, Venus passes across Earth's view of the Sun only every couple hundred years, yet TESS's cameras are seeing many planetary transits among the hundreds of thousands of stars it takes streaming long-duration videos of, and you know what that means. It means there must be hundreds or thousands of times more planets than are observed by the transiting method. It is, therefore, an inescapable conclusion that every star has planets. Planets are everywhere. And now, the James Webb Space Telescope, with its giant 21-foot, 4-inch wide mirror, is entering the search. It is a technological marvel, a wonder of the modern world, a miracle of advanced engineering. Anticipation is reaching a fever pitch. But with the heightened anticipation comes an almost equal amount of trepidation. And some things can still go wrong before the James Webb Space Telescope returns its first pictures. After the Hubble Space Telescope, for example, was launched in 1990, a repair mission had to be launched in 1993. The mirror on the Hubble was not very well inspected, and its pictures were very blurry. Astronauts had to go up and execute a spectacular spacewalk to fix the mirror. After the fix, the pictures Hubble sent back were more precise than it was ever designed for. This is how an improved model appeared. That cannot happen with the James Webb Telescope. The Hubble orbits the Earth and is accessible to astronauts. The James Webb Space Telescope orbits the Sun and is well beyond the Moon, out of the reach of astronauts, because there is no spacecraft equipped to carry them there. It cannot be manually fixed if something goes wrong. Adding to the challenges, the James Webb Space Telescope has only one onboard camera to inspect any damage it may suffer or mechanical malfunctions that might develop in the harsh environment of interplanetary space. Any remote fixes will need to be done blind from Earth. The James Webb Space Telescope is now fully deployed. The 18 mirror segments will need to be aligned to produce a single image. This critically important process will take several months to complete once the telescope is fully deployed. 70 of the first 286 observation assignments of the telescope target exoplanets. Using data from previous exoplanet searches, it will not have to waste time searching for exoplanets. Their locations and orbits are already known. The James Webb Telescope will go right after them. The James Webb Space Telescope is not an optical telescope in the same sense as the Hubble Space Telescope or any ordinary telescope that sees visible light. It sees infrared light. The pictures of planets are expected to be bright dots, somewhat fuzzy if they have atmospheres. The spectra of the planets will yield the most information about the exoplanet. Any gases around an exoplanet will absorb some starlight as the starlight passes through the planet's atmospheres. Suppose there is methane in the planet's atmosphere, oxygen, or carbon dioxide, the gases that most indicate life. In that case, the James Webb Telescope will be able to pick them up by spectroscopic analysis. An entire portrait of the exoplanet can be formed from the infrared information, its temperature ranges, atmospheric content, the likelihood of liquid water, and even the probability of life. And that's a big deal. The James Webb Space Telescope has other missions to perform too. It's assigned to examine star formation and planet formation in nebula in the Milky Way. Understanding how solar systems form is part of the search for another Earth. By detecting infrared light, the James Webb Space Telescope will peer to the farthest away galaxies whose visible light gets blocked by dust and gas. These distant galaxies were formed shortly after the Big Bang. Galaxy formation is an essential mission for the James Webb Telescope. These most distant galaxies are accelerating away so fast that the light they emit is stretched below the frequency of the visible spectrum, into the infrared. The Great Telescope can see these previously invisible galaxies. We hope to learn about the mysterious dark energy that is causing the universe to expand at an ever-increasing velocity. Hope is high that the James Webb Space Telescope will significantly expand our knowledge of this amazing universe we all live in. A new super-Earth has been spotted by astronomers, and it's quite intriguing. This planet, called TOI 715b, is about 1.5 the size of Earth, which is why it's called the super-Earth. It's also relatively close to us in space terms, only 137 light-years away. For comparison, most exoplanets are hundreds of light-years away, and all the interesting stuff, like black holes and nebulas, are usually more than thousands of light-years away from us. So, could it be habitable? The habitable zone is an estimate of where a planet might have the right conditions for liquid water. This is what we call some distance from the star where the temperatures on the planet should be okay-ish and water should stay liquid on its surface. It's not super precise because it depends on a bunch of factors like the type of star, how reflective the planet is, its size, and so on. Also, just being in this zone isn't enough for water to actually be there. The planet also needs the right kind of atmosphere and a few other things. So, we invented a stricter definition in 2014, the conservative habitable zone. It's a more precise term defining the best candidates that have liquid water. Otherwise, we get too many potentially habitable planets that are not actually habitable at all. The CHZ is based on how much energy a planet gets from its star compared to Earth. If a rocky planet gets between 40 to 85%, it's considered to be in the CHZ, no matter how far away it is from its star. These planets have a higher chance of being habitable. And yes, TOI 715b is located there. This super-Earth orbits the M-type star, also called red dwarf. It's a star that's much smaller and cooler than our Sun, about a quarter of the Sun's size and mass. But if the planet is located in the habitable zone, it's actually a better option for life. Red dwarfs live much longer than our Sun, a yellow dwarf. This also means that they have more time to form little creatures on their planets. And this red dwarf really is older than our star. Our Sun is 4.6 billion years old, and this star is 6.6 billion years old, give or take a few hundred million. It doesn't have much magnetic activity, so it's not dangerous. It doesn't flare up like younger red dwarfs. These flares can be super strong and might even hurt planets by taking away their atmospheres. Although some planets around it do have thinner atmospheres, it seems like this red dwarf has already gone all out. These red dwarfs are where we're looking for planets that could support life right now. Our super-Earth is really close to its star, zooming around it in just 19 days. Since the star is small and the planet is so close, the planet passing in front of its star happens a lot and looks really clear. This makes it easy for telescopes like the James Webb to study its atmosphere without needing too much time. Now, speaking of the James Webb Space Telescope, it's bringing us into a new era of understanding distant planets beyond our solar system. Imagine being able to see what gases make up the air on a planet millions of light years away. James Webb will help us to find worlds that could support life. Right now, it's trying to figure out whether TOI 715b has an atmosphere. If it does, its atmosphere might be easier to spot compared to a planet that's drier and denser. And then we might get even more height because it would look like a good place for life. On top of all that, there might be another planet in this system, also in the habitable zone. We're not sure whether it's really there, it's just a candidate with a crazy name. But if it turns out to be real, it would be about the size of Earth. Also, it would be the smallest planet in the habitable zone ever spotted by the TESS telescope. Now, another cool thing about TOI 715b is that it cannot just have water on it, but be an entire water world. An ocean planet is a type of planet that has an ocean covering its surface or has subsurface oceans. They might not have much dry land because the water can cover everything. Sometimes the entire planet can be covered in other liquids, like lava or ammonia. When it comes to planets outside our solar system, we can't see surface water directly with our current technology. Instead, scientists look for water vapor in the atmosphere as a hint there might be liquid water below. And of course, we wonder if these planets can have life, hopefully not in the form of Leviathan-like monsters. Our models show that planets with oceans might be pretty common in our galaxy. This means there could be lots of ocean worlds out there waiting to be discovered. But the most important part about TOI 715b is that it's in the so-called small planet radius gap. If we give the planets a lineup, there will be those that are bigger and smaller than Earth. But there's a sudden gap in planets that are about from 1.5 to 2 times bigger than ours. Where are they? This gap is interesting to scientists because it tells us something about how planets form and change over time. It's not that planets don't form in this size range. They actually start off larger and then lose some of their mass, like a balloon gradually deflating. Perhaps it happens because of how they orbit their stars, with stars blowing away some of their mass as they dance around it, as our Sun does with gas from comet tails. This gap holds a lot of mystery, and planets, like our new super-Earth, are clues that could help us unravel it. We aren't sure whether it exists around red dwarfs. Maybe it's a gap in how dense these planets are, rather than in their actual size. So studying our discovered planet is even more interesting. It'll help us learn more about distant stars and their planets. Now, I mentioned TESS a while back. NASA's TESS, Transiting Exoplanet Survey Satellite, has been in space for 6 years now and has been incredibly successful. NASA launched TESS because we already found over 5,000 planets orbiting other stars, mainly thanks to the Kepler telescope. But Kepler mostly found large planets, not necessarily like Earth. We decided to focus TESS on finding smaller Earth-like planets around nearby bright stars, making them easier to study with future telescopes. Here's how it works. The camera observes stars and looks for changes in their brightness. If the brightness suddenly drops for a while and then gets back, it could mean there is a planet passing in front of it. But stars can dim for other reasons too. For example, flaring up or having dark spots on their surface, which is why we need to be careful with this data. TESS shows us the size and orbit of these planets. Then ground telescopes help determine their mass. With these 3 parameters, we can figure out what the planets are made of and if they're rocky like Earth or gassy like Jupiter. Yeah, you want to avoid Jupiter after taco night. One example of TESS's discoveries was the TOI 700 system. There, it discovered its first ever Earth-like planet, TOI 700d. This exoplanet also orbited a red dwarf, and it's even closer to us, about 100 light-years away. Unfortunately, it's unlikely to be habitable because the temperatures there are crazy. Another big discovery was made in the AU microscopy system. TESS discovered a planet about 4 times the size of Earth and another nearly 3 times Earth's size. This system has become a key area for studying how stars and planets form and change over time. TESS has also spotted a variety of other exciting finds, including supernova, hot worlds, and so on. And as it enters its 6th year, we can only expect more exciting findings to come.